Hello, good afternoon, everyone. I think it's 12:30. It's a good time to start. So welcome to SensorRig 2021 conference series. This is our first conference presentation this year. I'm Amin Rashid Chaudhry, moderator for SensorRig conference series. The SensorRig is a multidisciplinary group of researchers with interests in sensor materials, methods, devices, and sensor applications for healthcare, environment, civil, petroleum, chemical industries, and military applications. This group provides an opportunity to exchange ideas, present early findings, and explore collaboration and interdisciplinary funding opportunities. Sensor rigs aim are to connect sensors, technologies, middleware, and applications, and to provide an interface between academic and industrial research. Today, we have Leland Nordin. He is a graduate student in the Electrical and Computer Engineering Department at UT Austin. Specifically, he has been graduate research assistant in Professor Dan Wasserman's group since 2016. His research involves monolithically integrating highly doped semiconductors, which are plasmonic materials in the mid-infrared, with quantum engineered mid-infrared active region for enhanced emission or detection. So let's enjoy the presentation on All-Epitaxial Plasmonic Optoelectronics for the mid-infrared. If you have any question regarding this presentation, feel free to ask after the presentation. Thank you.
Thank you for the introduction. I think you're going to need to give me the ability to share my screen, or else it's just going to be my face and no slides. Thank you. Okay. Okie dokie. So thank you for the kind introduction. As was stated, my name is Leland Nordin, and I'm a graduate student in the Mid-IR Photonics Lab led by Professor Dan Wasserman. Today I'll be talking about our work on integrating epitaxial plasmonic materials with optoelectronic active regions for enhanced performance in the mid-infrared, specifically emission, but I'll try and lean it a little bit more detectors, and my work actually leans a little bit more detectors as this is the sensors rig. So before I get into my talk, I'd like to give a brief overview of what I'm going to talk about today. First, I'm going to give an introduction. I'm going to talk about plasmonics. What are plasmonics? What does the field of plasmonics look like? And what is some of the previous work in the field of plasmonics? And then also the mid-infrared, some of the applications in the mid-infrared, and what, in our group at least, what spectral range we define as the mid-infrared. I'm then going to talk about designing optical materials in the mid-infrared, specifically these highly doped semiconductors, and how we can tune their plasmonic response across the mid-infrared. As a complement to that, we also need to be dealing with optoelectronic active regions in the mid-infrared. So I'm going to talk about how we can design those and the kind of flexibility we have to the electronic structure as well as the actual optical response. And then finally, I'm going to talk about our work merging these two fields, so plasmonic and highly doped semiconductors, and then also these actual optoelectronic active regions for enhanced emission and detection. Then I'll have a conclusion and some future work. So first, the introduction. So plasmonics is essentially the study of metal materials, but specifically metal materials around the point where they turn metallic optically. So right at the transition between them looking like a dielectric as far as their optical response and a metal. The two modes that are often leveraged for plasmonic phenomena are SPPs, or surface plasmon polaritons. This is a bound mode at a dielectric metal interface. And the dispersion relation shown below tells us the phenomena, or tells how that mode is going to go. And then the other mode that's often used in plasmonic research is localized surface plasmons. These are a similar mode to the bound mode that is the SPP, but it's bound instead to a small nanoparticle. Both these modes have been used for a handful of really impactful work as far as ultra strong light matter interaction. They've been used for subdiffractive sensing of biological particles, nanolasers, optical interconnects that are below the diffraction limit, et cetera, et cetera. A lot of this work, especially the initial work, was using noble metals in the near IR and visible. And one of the struggles that this near IR visible plasmonic work has had is actually integrating these plasmonic materials, specifically these noble metals, into a lot of the optoelectronic active regions because the nanoparticles, for example, putting those into a P contact layer often actually degrades the performance of like a LED enhanced by plasmonic phenomena. So in this talk, I'd like to present our work in the mid-infrared where we are able to more seamlessly integrate these plasmonic materials. So that leads me to now talk about the mid-infrared. The mid-infrared is a spectral region from around 3 to 20 microns. Everything really absorbs in the mid-infrared, making it an excellent wavelength regime to work in for chemical sensing, so much so that it's actually nicknamed the chemical fingerprint region. This is used in medical diagnoses for breath analysis, pollution monitoring from plumes coming out of factories and making sure they aren't burning anything they're supposed to or not supposed to be burning, infrared astronomy, and then also the mid-infrared is home to 2 atmospheric transparency windows, one from 3 to 5 microns and one from 8 to 12 microns, making it a great candidate for free space optical communication. Which leads me to my next mid-infrared example. Everything emits in the mid-infrared. And a canonical example of a mid-infrared application is thermal imaging or night vision, which leverages these atmospheric transparency windows to view either humans, which emit around 10 microns, or planes, trains, and automobiles, which will emit closer to 3 to 5 microns, that other atmospheric transparency window. So there are some significant applications or important and vital applications in the mid-infrared. Are there ways that we can leverage plasmonic phenomena to enhance emitters and detectors and make better technologies to attack these applications? Well, let's look at what sort of candidates we have for plasmonic materials in the mid-infrared. What we generally actually use is not the noble metals, because in the mid-infrared, those look a lot more like perfect electric conductors, and you don't get these tightly bound modes anymore. What we actually use are doped, highly doped semiconductors. Essentially, we're able to put in so many free carriers via doping that they start to act like metals in the mid-infrared. We do this via molecular beam epitaxy, which is a growth technique where essentially you spray paint 3-5, in this case, semiconductors onto a substrate, and you have fine control of the doping, the thicknesses, and then the constituent alloys. We do this in collaboration with the Leys laboratory and MRC, Professor Banks' lab. And shown here is reflectance versus wavelength for a handful of these doped semiconductors. The dotted line here is the plasma wavelength, which is the wavelength at which the material turns from more dielectric-like, so you can see not very reflective, primarily transmissive, to highly reflective for these longer wavelengths and more metallic. So the plasma wavelength is right around where you can actually couple to some of these plasmonic phenomena I talked in the beginning, the surface plasmon polariton or the localized surface plasmon. And we can, but in the mid-infrared, unlike the near-infrared where you're stuck with whatever the noble metals plasma wavelength is, we can actually tune it for whatever application we want. If we wanted something in the longer wave or something in more towards the mid-wave, we can tune it simply by the doping of the semiconductor. So that is the plasmonic side of things. What about the actual optoelectronic active regions we typically use? So often we're using type 2 superlattices, and then let me define both those parts separately. First, the type 2. In heterostructure engineering, we have 3 flavors of band offset available to us. Type 1 straddling, this is a conduction band and valence band of 2 materials. Type 1 straddling, where one narrow band gap material is bookended by a wider band gap material. Type 2 staggered, and type 3 broken, where they're actually slightly offset, the 2 materials. So that's the type 2 part, really type 2 or type 3. And then the superlattice is if we stack these type 2 band offsets over and over again next to each other, we form a series of coupled quantum wells that are actually coupled via tunneling, and you can form electron mini-bands and hole mini-bands whose effective band gap can be narrower than the constituent materials. We have grown a lot of these, and as you can see, we're able to tune this effective band gap across the mid-infrared, no longer being bound by the constituent materials band gap. So this is photoluminescence for a handful of type 2 superlattices that we've grown in the lab. And just like the doped semiconductors and their plasma wavelengths, we can tune all the way from 5 microns in the mid-wave infrared all the way out to 13 microns. So we have this really, really rich system to tune not only the optical response of our doped semiconductors, but also the electronic band structure of our superlattices. So what can we do as far as putting them together and making actually enhanced emitters or detectors and plasmonic optoelectronic devices? Well, the first question comes to mind is that these semiconductors, optoelectronic devices specifically, often leverage high crystallinity. And we're incorporating all these dopants, does that compromise the optical quality and ruin our emission or potentially ruin our detection or ability to collect photocurrent? So the first experiment we did was we grew 2 samples, one type 2 superlattice on a undoped virtual substrate, and then another one on a highly doped plasmonic material substrate. And that's what's shown here. And then we performed photoluminescence measurements on both of them. On the left is the control structure, wherein we grew the T2SL on top of a undoped substrate. And then on the right is the T2SL grown on a highly doped substrate. And you can see we actually get better photoluminescence, suggesting our optical quality is as good, not necessarily better, because the actual physics for why we see an enhancement in photoluminescence is due to the resonant cavity and then also the additional photonic density of states from the SPP mode. And this theory associated with why we see the emission enhancement that we do, we worked on with our collaborators at UMass Lowell, Professor Victor Podolsky's group, and it's a product of the Z component of the pointing flux, which is that S sub Z, and then also the Q tilde, which is your Purcell enhancement, so this additional photonic density of states. Essentially, though, we were able to accurately model this photonic or this photoluminescence enhancement. It's about a factor of 6. And then for the actual implications for optoelectronic active regions, it seems as though we can grow high quality crystal on top of plasmonic materials, and we don't see any degradation in quality, which in the near IR vis world, people have struggled a little bit more to do, especially with some of the embedded nanoparticle work. So we can grow these type 2 superlattices on top of plasmonic materials. What can we then do as far as actually enhancing optoelectronics? That is sort of the name of the talk. Well, if we use or leverage that high reflectivity, we might be able to grow a resonant cavity, similar to how that photoluminescence was enhanced. So if we look at the detector thickness versus wavelength for just one of these T2SL absorbers on top of a gallium nitride substrate, you can see we have rather low absorption efficiency, around 10 to 20%, where typical infrared detectors are upwards of 60%. This is almost completely a consequence of the fact that the hole in electron wave functions are spatially separated in a type 2 superlattice. So they have a rather low absorption coefficient, meaning that it would be beneficial to enhance their absorption through some sort of plasmonic enhancement. This isn't a totally fair, sorry, I clicked on the zoom. This isn't a totally fair comparison, because actually people often metalize one side and then detect through the substrate, and you get a double pass configuration shown here. So you get a little bit increase in, let me shrink this down so it's not blocking everything. A little bit of an increase in absorption, but you still need to grow relatively thick absorbers, and generally speaking, your dark current or your noise in your detector scales with your absorber thickness. So even though you're growing thicker and thicker absorbers, you're also incurring more and more dark current. So what about if we grow one of these on top of our plasmonic ground planes? Well, you can see that we are able to form a resonant cavity with the air semiconductor, highly doped semiconductor ground plane, and we can get rather significant enhancement of absorption in the long wave infrared, around 8 to 12 microns, something that we do not see in the double pass configuration. And then I'd also like to note there's this even thinner first order Fabry-Perot mode, or around 300 to 500 nanometer absorber thicknesses that we could leverage to actually couple into surface plasmon polariton modes, and I'll talk about that a little bit later. But to actually demonstrate this is all simulations, actually demonstrate this, we grew 2 detectors on top of N++, and then also 2 control structures targeting 2 enhancement wavelengths, one at 8 microns and one at 10 microns. Shown at the top of the actual structures, they're just PIN optoelectronic devices, and then shown below is both our simulated absorption for the enhanced devices and their controls, and then our actual experimentally measured external quantum efficiency. So we grew these samples, we fabricated in the mesas, we metallized the top and bottom, and then we perform spectral response characterization, responsivity, and EQE. And you can see our simulations match our experiment extremely well. We hit our target wavelength very well, around 8 microns and 10 microns respectively. And then our actual enhancement comes out to about 4.5-ish. We realized 45% EQE for the 8 micron target, where it's only 10% in the control, and then around 2.7 in the 10 micron target wavelength. And again, it's about 10% for the control, but about 27% for the N++ enhanced, or the doped, highly doped semiconductors. So at the beginning of this talk, though, I talked about these SPP modes or these LSP modes, and I've really only shown phenomena leveraging the high reflectivity of the doped semiconductor. So there's a way that we can actually couple to surface plasmon polaritons. Well, in 2018, our group had a theory paper doing just that, where we would have a optoelectronic device grown on top of one of these highly doped semiconductors, and then an antenna, which is actually a gradient coupler to provide the momentum to couple into that surface plasmon polariton mode. And if you look in figure H here, this solid red curve is the simulated absorption in that active region, and it's around 50% long wavelength light and only about a 300 nanometer absorber. So much, much smaller than the diffraction limit, about lambda over 30. So we are now working on actually growing and fabricating these detectors, and we've also now given them a fancy name, Plasmonic Infrared Quantum Engineered Ultra Thin Epitaxial Detectors, or PEAK. And then shown on the right is the actual measured reflectance from these detectors with these gradient couplers patterned on top. We ended up using patch antennas, so we didn't have any polarization selectivity. And then also simulated results using rigorous coupled wave analysis. This is another simulation package from our collaborators at UMass Lowell, Victor Podolsky's group, and you see a very good match between our experiment and simulation, and then a rather significant dip in reflectance around 10.7 microns, suggesting coupling to some sort of mode. If we then use that same software package to calculate the fields, you can see a rather bound mode at the plasmonic semiconductor absorber interface, suggesting that we are coupling to some sort of SPP. So same story as the RCE detectors. We fabricated them into full devices and performed spectral characterization and external quantum efficiency. And then I also have a nice SEM micrograph in the top left inset of our external quantum efficiency plot. And you can see we're able to realize around 42% quantum efficiency in only a 317 nanometer absorber, which was much, much, much smaller than the wavelength, the free space wavelength of light. And it amounts to about a 14x enhancement. So over an order of magnitude enhancement in EQE relative to if we just grew this same thickness of absorber, this detector, on a non-plasmonic ground plane with no gradient couplers. And as I mentioned earlier, dark current scales as your absorber thickness. So one would expect with this really, really thin absorber, we'd get a reduction in dark current and therefore a reduction in noise. So shown on the right is actual dark current versus temperature of our peak detectors. And you can see around 130 and 120 Kelvin, we actually are below mercurium cadmium telluride, which is the state-of-the-art infrared detector and has been so for the last 60 years. So with this plasmonic enhancement, we're able to realize comparable EQE with lower dark current than state-of-the-art infrared detectors. So now I'm going to conclude my talk. The mid-infrared is an especially exciting wavelength range to work with plasmonics because we're able to monolithically integrate and seamlessly integrate these plasmonic materials with these semiconductor active regions. And we've been able to show enhanced efficiency, not only in terms of emission, but also absorption. We're very lucky because the 6-1 semiconductor family, indium arsenide, aluminum antimonide, gallium antimonide, we're able to integrate and grow doped semiconductors in the 6-1 semiconductor family and these emitters. Doing so, we've been able to demonstrate enhanced emission, we've been able to demonstrate enhanced detection, and we've been able to do so in ultra-thin absorber regions, beating state-of-the-art infrared detectors. Future work will leverage additional functionality. There's a rich dispersion space with any of this plasmonic phenomena as far as angle tunability, and then also the propagation length of the surface plasmon polariton modes, or in some cases, long-range surface plasmon polariton modes, where you can imagine some ideas for hyperspectral imaging or dual color detection or what have you. So with that, I'd like to thank you all for listening to my talk. My funding agencies, NSF, the MERSEC, and then of course the Microelectronics Research Center up at the Pinkel campus where the majority of this research was performed. And then of course the RIG committee, both the students and the professors, for inviting me to give a talk.
Thank you, Leland, for your beautiful presentation. This was really interesting, especially I also work on the similar SPR region. So this is really interesting to me. So now let's give us our audience the floor to ask questions. So there is a question from Dimitri Kirev. He's asking, he's thanking you and saying, you mentioned mid-IR allows to sense certain molecules. Can you measure those molecules selectively?
Guess I would, thank you for the question. I guess I would ask, what do you mean by selectively? I mean, absolutely you can functionalize, I think, selectively some of your plasmonic particles for some of these more like biological sensing applications. That stuff I'm not as honestly familiar with, but for at least selectivity in terms of for certain molecules, not necessarily selectivity for any of my work, because we're not like covering our samples with any sort of fluid or anything like that. And that's what I more think of when you say selective molecule detection. That being said, we are working on wavelength selectivity in terms of some of these plasmonic modes. So there's different flavors of plasmonic modes that you can leverage, specifically long range and short range surface plasmon polaritons, which we're going to have a paper coming out shortly. It's been accepted, and I'm supposed to be looking through the proofs right now, where you can leverage the dispersion of a long-range and short-range surface plasmon polariton to have dual color and it be a little bit more wavelength selective, or just leverage one of them and then be more wavelength selective. So in that sense, if you knew the absorption feature had a specific spectral position associated with it, you could then design your plasmonic system to target that. And then where you've designed that target wavelength, you could absorb at a specific part in your detector. It's a good question.
Yeah, thank you. Yeah, cool.
So there is another question on the chat. What are corresponding thickness of the state-of-the-art MCT detectors? Also, what are the current limiting factors for the dark current of these ultra-thin devices?
So thank you for the question. Yinan's in my group, so he kind of has home field advantage on asking me questions. The corresponding thicknesses for a lot of the MCT detector is generally the wavelength of light. They often use, depending if they're photovoltaic, so they're actually grown with MBE, or if they're photoconductive, so they're grown with LP or liquid phase epitaxy. But often they're grown to about 10 microns. So being a 300 nanometer absorber versus a 10 micron absorber, we're winning there as far as material. And then there's actually this big push recently that ROHS, environmental concerns with mercury and cadmium in Europe especially, is starting to bar the sale of MCT. So there's a significant interest in getting these 3.5 semiconductors off the ground and actually having them be a little bit more competitive with MCT. And then for the ultra-thin devices, if you actually look at the activation energies as a function of dark current, it seems as though we are Shockley Reed Hall limited, which, because they're ultra thin, that could just be an effect of the band bending there, and we're always going to be a little bit Shockley Reed Hall limited. With that even said, Shockley Reed Hall is generally associated with material quality, so if we just get better at growing these, we might see them reduce in dark current. But the real point here is that we are no longer bound by the strong relationship between absorption coefficient and detector thickness. We can kind of tune those independently with this plasmonic phenomena.
Thank you, everyone. If you want to ask more questions, please feel free to unmute yourself, as Siang is saying on the chat. I think no one has any more question. If you have any more question, please feel free to email us or Leland.
Yep.
If you email us, we'll forward it to him. And thank you, Leland, and our audiences for their valuable time. Please feel free to send any comments or suggestion to our email address in sensorigstudents@utilis.utexas.edu, Also follow us on Twitter. Our Twitter handle is SensorRig. Now, I would like to invite our audience for the next presentations. Our next presentation is coming on 26th March 2021. It's starting at the same time, 12:30 to 1. You are all cordially invited to join this presentation. Thank you.
Thanks again, everybody, for coming to my talk.
Thank you, Leland. Thank you, everybody.
Thank you, everyone. We'll end our session for today. Thank you again for joining us.